Hi, this is IPC Interprocess Communication Part 2. Let us now go deeper into some of those IPC principles, and these are the topics that we will be covering now. Before we get into the core of IPC, let us understand the key definitions which are commonly used in the IPC mechanisms or IPC related topics related to OS. Now, first of all, process interactions that I have already mentioned about it, processes unaware of each other. That's two different user processes running on a Unix or Linux server is a good example where they don't even know the existence of other processes, though their presence will indirectly impact their own completion, time taken for completion of its own activities, or the time that it is given by the OS on the CPU. So there may be a load related to different processes being there. For example, if you are trying to book a ticket, a train ticket or a flight ticket, and during a peak festival season, there are going to be many people accessing the same website and trying to book tickets. So you will not know which are the processes or who are the users trying to block the tickets or for which travel they are doing. But you know that it is indirectly impacting you because the same server is being shared by multiple users. So these are the processes unaware of each other, but they have an impact of their own performance getting affected because of the presence of other processes. Okay, but they don't do any cooperative work. They do independent work. Every user wants to block some tickets for some airline or some particular sector, but they are getting impacted because of the sharing of resources in the system. So it's a multi-programming, multiple independent processes running in the system. There can be batch jobs or interactive sections or a mixture of both. Okay, interactive section means you are trying to book a ticket, which is an interactive process, whereas batch job means suppose you are trying to watch a video or a live match where you are not doing anything interaction with the streaming which is happening, but many users sharing it is is one kind of a example of a process. Now processes indirectly aware of each other. So totally unaware is one thing, indirectly aware of each other. One good example could be that we are trying to access, Arduino IDE is running and you have multiple boards you are connected to a USB interface. Then there's one single process, but they are accessing an IO which is shared by multiple processes. They know that there are many processes in the system. They may be accessing the IO, which is common, like USB interface. So indirectly aware of each other, because you may see that when you are opening a Arduino IDE, you will see that COM3 and COM4. Suppose your two boards are connected, IDE will show up both the COM ports. So you have to choose which board you are talking to, which COM port you are trying to upload a software into. So this is one a good example of processes which are indirectly aware of existence of other processes, right? Such process exhibit cooperation in sharing a common object. It's like in our case, it's a COM port which is being shared by them, but they don't actually interact so closely that they don't exchange information, but they are using the same laptop interface and USB interface to talk to different boards. But Arduino IDE is a common interface, a common software which is being used by different boards connected to the same system. Okay, that's one good example of indirectly aware of each other. Now, processes directly aware of each other. Then suppose you are creating a process, then you are creating some threads or your child processes you are creating, and then they exchange some information to accomplish something, or they access the same file and they both of them operate on the same file and update each other, some information. So they are directly aware of each other, and they need to make sure that they don't step onto each other's activities by mistake. So there have to be IPC mechanisms used here where processes are cooperating processes and they are aware of each other, right? So some of the keywords, now one by one let me go into that. Atomic operation. Now what is atomic operation? A thing that is being done without any interruption. Okay, atomicity. We know, we heard this word is used because those time we think that atoms cannot be split. Okay, now no longer it is true, but still I am saying that atomic operation here means that a sequence of one or more statements in the say in here I mean by statement means it's not a C instruction. At C instruction cannot be made as a atomic unless you provide some mechanisms to do it. And here the statements could mean assembly instructions also. Okay, that appears to be indivisible. That means they need to be operated or they need to be executed without any interruption in between. That they should continue to do, and no other process should interfere in between. That is, no other processor can see an intermediate state or interrupt the operation. So they once it started, it should complete. Okay, so that is what is called atomic operation. Okay, it's like a flight takes off, you can't make the flight to stop in between, freeze in between, and then take some action there. So it has to land somewhere, right? So that is an atomic operation. Though many things go from landing to or takeoff to landing, but still it needs to be no interruption should happen. Thankfully, right? So critical section. What is critical section? A section of the code. Okay. Always remember, critical section means a piece of code operating on a common data. So a section of code within a process. So naturally, no code can be executed unless it is in the context of a process, right? Because everything is a process in a system. If we are to execute something, it needs to be a process. Remember, any code that you run, any program you run, even ls command you give it on a terminal is a process. So even if you open a terminal, it's a process, and then you execute a program, it's a process. So within a process, an instruction is executed. That instruction could be a set of assembly instructions corresponding to a particular higher level language. So that requires access to a shared resource. It could be a data or a linked list or maybe a file or maybe an IO device. Okay, or maybe a hard disk, which is being shared by many processes, and that must not be executed while another process is also accessing the same shared resource. So when I say that a linked list is being updated, then I want to make sure that only one process is accessing the linked list, so that they update. If it is adding a node or deleting a node, it updates both previous and next pointers and make sure that they are all pointing it properly before any other process try to do something with the linked list. So that's a critical section, a piece of code which is operating on a shared data, okay, which needs to be protected against multiple processes doing the same, accessing that, or executing a piece of code which will also be accessing the same data. See, suppose let me tell you a process P1, okay, is trying to add a node into the linked list. So it may be executing a function which is called add node. Okay. Now at the same time, some other process P2 wants to delete a node. Okay. Maybe it would have been passed with the node pointer and it is executing a delete node. See, the code that is being executed by the P1 and P2 are different because it is executing two different processes, add node, and this is executing a delete node. But when it is executing, we need to make sure that we call this program as a critical section. Why? Add node is also accessing the linked list. Maybe it will look for this particular node being passed, locate that node, and then or location, suppose if it has to be added to the front of the linked list or end of the linked list, okay, then add node has to either traverse the linked list to find out the place where it has to be added, or it could be that add node has to be based on the value that the node has. Okay, if it is the linked list is maintaining a list of numbers which are in the increasing ascending order or descending order, it has to go through the particular linked list and then add a place, find a place and then add it. Now this particular operation is a critical section. Why? Because it is operating on the same linked list. Okay, it's not the code we are protecting, but we are protecting the code because the code is where the action is being done, but data is passive. We are operating on the data which is shared between two different processes. Okay, so delete node also has to be protected in the sense it should be in the critical section, and add node is also a critical section, but they are two different piece of code operating on the same common data. So that's what I mean by which is a critical section, the code which is operating on a common data. Deadlock is a condition wherein no process can proceed further. Okay, they are waiting for some other event which is also waiting, blocked because of some, say because of the same process which is being blocked. A situation in which two or more processes are unable to proceed because each is waiting for one of the others to do something. Okay, this process is waiting for this to complete, this process is waiting for this to complete, and this is again waiting for this to that. So all of them are stopped, nobody can proceed further. So that's a situation where deadlock happens. Okay, live lock is a situation wherein each process tries to make a move, but it is not progressing as a end goal is not achieved. Okay, it is still making a waste of. It's like in a football match, you may see that they keep exchanging the ball between two players, but they don't never go near to the goal post, and they just do keep doing it because it's actually maybe it's a strategy to make sure that the opponent team is not getting a chance to get the ball, but still they are not progressing further. The time is lost, either goal is no goal is scored, or they are not making progress towards the goal score, but they keep exchanging the ball between two players. So that's like a live lock wherein they keep doing something but not progress is made, no progress is made. Mutual exclusion, that means when I say the delete node or add node, that should be that code has to be mutually excluded. That means two processes will not be allowed to execute that. Or instead of saying even the code, the data whatever is being accessed, it should be mutually excluded. Any program, either add node or a delete node, if trying to change something onto the common linked list, they should be mutually excluded. The processes should be mutually excluded. That's called mutual exclusion. The requirement that when one process is in a critical section, that means one is in a delete node, the other process should not be allowed to enter a add node. Okay, critical section, that access the shared resource. Remember here, shared resource means the linked list. No other process may be in a critical section. Now this critical section and this critical section are on two different code base. Okay, it could be two different part of the code. One is add node and one is delete node, but they are interrelated because they are accessing a common linked list. Okay, what is being passed to it is the same linked list node. Code may be different, but code may be same, but what is being asked, the linked list, what it is accessing, they are same. Okay, both of them are trying to access the same linked list. Okay, the common shared resource is the to be considered. Okay, race condition is something like when one process is changing a variable and another process is reading it. Now while this is getting updated, it is reading the data, okay, and then updating it and putting it back, somebody else is reading it, then they are not going to get the correct value because it depends on when the process is trying to read. So that's a race condition. Starvation is something like you, maybe some low priority process is not getting a CPU to run at all. That means it's starved. Your process is starved and it's not able to make a progress because CPU is not allotted to that. Okay, these are all some key words that you should be aware of when you are talking about or reading about IPC. Now, what is mutual exclusion and the critical section, which I have already explained? Let me explain that. Now, errors due to concurrent execution. See, all these problems happening because there are concurrent processes in the system. Where if suppose there was a single process and there is only single unit of series of execution, then there is not going to be any issue. And whether you have a single core or a multiple core, doesn't matter. If multiple processes do not run or if they don't operate on the same common data, then there is no issue. But the issue happens only when you have concurrent execution of cooperating processes. Again, that is very important. May result in timing errors detrimental to the system's reliability. Why is it not reliable? Because what you read may be not a stable value. It could be that at the same time somebody else is updating it. So synchronized errors are often introduced between processes as opposed to within a process. Okay. Normally, there is. I'm not relating these two. I highlighted it because there are two different concurrent processes which are not synchronized, and they are running on either single core or multiple cores or at a different speed. Then error is likely to happen if they are accessing the common data, and then there may be an issue with the synchronization errors because you want some process to complete something and then pass on to the result to somebody else. So it is between processes as opposed to within a process. Within a process, it's a single stream of data, right? Single stream of execution, single sequence of instructions being executed. So there is no synchronization error possible. It is only possible between processes. Okay. So for instance, neither of two sample processes is sole cause of the timing problem. Now, when these problems happen, all these two processes which are involved or they are not doing anything wrong. The problem happens because they are running in parallel and they are trying to access something common. Okay, please remember, it's nothing is wrong. The way you write a program, if they only one process runs, there is no issue. But when both of them run, there is an issue that needs to be taken care of by properly using the IPC mechanism provided by the OS. Okay, you have to be careful when you are writing a multitasking application, multi-process applications, and you want to actually writing cooperating processes and you want to access a common data. You need to think about the topics or the IPC mechanism that being explained here. Okay, you have to use them in your code. It is the concurrent execution and the unpredictable interleaving of the two causes the issue. So what is mutual exclusion? One at a time. Okay, if you are updating the linked list, only one process should be allowed to update the linked list. Okay, where if you are maintaining two different linked lists, yeah, you can go ahead and update it, no issues, as long as they are not the same linked list. But don't think that am I operating on one particular node in the linked list or different node, doesn't matter. You need to be very careful about entire linked list because you don't know which node at a time you will be using. So, but two different linked lists if you are updating, they need not have to be protected against each other. They can be run in parallel. So, critical region is the area which is the piece of code which is operating on a common data. So mutual exclusion is in which a single process temporarily excludes all others from entering a critical section. That means what you should do is if there are multiple processes trying to apply, maybe add node is being called by somebody and delete node is being called by someone else, some other process, and find a node is being done by some other process, then you need to make sure that only one operates at a time. So you have to make other processes wait. Okay, it should be blocked state and only one is allowed to execute the program. Now, one good example, a simple example here, instead of linked list, imagine a single variable count is being updated by multiple processes. You are you have a count plus plus here. I will call it a C plus plus. It's not a language, but I'm saying C is a variable here. So I am doing C plus plus here. Okay, it's count plus plus. A count variable C I'm calling it as. So when I am doing it, what is happening is you need to have a critical section here. Enter the critical section. That means some mechanism which we will be start talking about to block any other process. Multiple processes coming will be blocked here. Only one will be allowed to come down. Okay. So what I mean by that, suppose this is a piece of code which is accessing the count to perform a C++, it will be expanded into this set of assembly instruction. That means load this count value into the some one of the registers, increment it and then put it back. So load, increment, store. Now these set of three instructions need to be protected. Now how do I protect it? I put some mechanism here. I am putting a macro here. Assume that before any process is accessing the count, I should make sure that they call enter critical section. Now when they do it, if one process is getting a chance to go further, then all other process which is executing this code will be blocked. Okay, so that means this will make sure that only one process get to come down execution. What happens to other processes? They will be blocked. Now they execute this, they increment it, they store it back, and the process leaves. Now when this leaves, this indirectly gives the it's because this CS critical section, whatever I am going to explain you about semaphore, is a single entity. So when somebody leaves it, it is going to say that I have done my job. Now, if anybody is waiting, let them, one of them, be allowed to enter. So that process will be allowed to enter the critical section. Now, which is the critical section here? The critical section is the piece of code which is in between these two macros. right? This set of three instructions. Why are they are critical? Because it is accessing the common variable. So, and it is being done in three stages, three instructions, and in between the instructions there can be an interrupt and changes could happen. So you may have two copies of the same copy of a variable on two processes, both of them updating it and then sending it back. You may miss one increment done by any process. Okay, that's what is a good example of a critical section. A sequence of instruction with a clearly marked beginning and end. It safeguards updating of one or more shared variables. And here only one variable I'm showing. It could be a linked list where both previous and next pointers are updated, or it could be a big data structure where you have many things to be updated. So when a process enters a critical section, it must complete all the instructions therein before any other process is allowed to enter the same. So once it enters the critical section, I can't say that okay, I'll come here, I'll stop here. Maybe somebody else is allowed to do it. It's like in a bank when you are getting into a locker, only one customer is allowed to enter the locker room. Though the customer is going to operate only his own locker, hopefully, okay. And then what happens is you don't allow some other customer also to enter the locker room to make sure that the safety of the person who is operating his own locker or her own locker is safe. Okay, so bank manager or somebody make sure that only one enters the locker, but you cannot go and sit and sleep there, right? You have to come out immediately because as fast as possible the other customer can enter the critical section. So what are the important things to remember here? Critical section means a piece of code you are executing, and you have to make sure that only one process execute that piece of code, and after that process leaves, another process can be allowed to enter that particular area of the piece of code to be executed. Now how do you decide something? Now critical section piece of code, you have to make sure that it is as short as possible. You don't try to make a large amount of piece of code wherein only one will process will be allowed. Now what will be the impact? Other processes trying to wait enter the critical section will be waiting for a longer duration. So that's one issue. And then there may be many processes trying to do it, so you need to make sure that the critical section is short and sweet. And what are the other precautions? You cannot, the process which is entering the critical section should not sleep there, right? You cannot go into the locker room and then make a phone call and talk for an hour, right? You have to be conscious of some other customer may be waiting to enter the locker room. So you have to make sure that you finish your job and come out quickly. So similarly, a process entering the critical section should make sure that it doesn't sleep, sleep for 2 seconds, or wait for some other event. Then if it is waiting for some other event, it has to be consciously designed because it could lead into a deadlock situation. Okay, these are the things you have to be very cautious about when you are designing the critical section and trying to uh, write a code within that area. So only the process executing the CS is allowed to access the shared variables. Shared variables only will be there in the critical section of the piece of code. So here the count is a shared variable. Okay, remember the count is a shared variable and the set of instructions is a critical section. And mutual exclusion is achieved by using a enter CS and leave CS. Okay, mutual exclusion is allowed achieved by allowing only one process to execute this set of instructions. So benefits of mutual exclusion: if a shared resource is a variable, mutual exclusion ensures that at most one process at a time has access to it and during the critical updates. Okay, and other things to avoid any temporarily inconsistent values. Consequently, other processes see only consistent values because only one is allowed to modify the shared variable. You will always see that consistent values are maintained. So it is true for even shared devices where you have printer which is being shared by multiple users. You will allow one document to be printed from one user, and then you allow another document print job from another user. So okay, you will not have a mix of two pages from each user coming out of the printer. It will be a chunk of pages from one user and then another chunk of data or papers from another user. So what are the principles of mutual exclusion? To be acceptable as a general tool, a solution to the mutual exclusion problem. Okay, whatever solution I am saying, enter the critical section I am providing or leave critical section is a solution that I am trying to provide to have mutual exclusion of a particular piece of code. Now, what are the things I need to take care? Ensure a mutual exclusion between processes accessing a protected shared resource. Okay. So if there is a shared resource, you have to make sure that mutual exclusion is ensured. Make no assumptions about relative speeds. When you are designing your software, you cannot design such a way that I expect the other persons to have completed this match. You cannot have an assumption of that because you don't know the relative speed, whether they got a chance to run or not. Even though they are cooperative processes, you still don't know what is the progress the other processes have made. So guarantee that crashing or terminating of any process inside of its critical section does not affect the ability of other processes entering the critical section. So suppose by chance a process in a critical section gets exited, or maybe somebody has given a control C and it exits, you have to make sure that it has acquired the log. I call it as a log. It acquired it and then went into the critical section. While holding the lock, if it dies or if someone else kills the process, we need to make sure that no other process is permanently blocked because one is holding the lock, no, he exited the system. So we have to have some mechanism to make sure that other processes are notified and they still recover from this loss, and then they continue further into their own execution. Okay, other waiting processes I'm talking about. So when more than one process wishes to enter the critical session, okay, then you have to make sure that they get the chance to enter the critical section within a finite time. Okay, though it is software dependent and application dependent, we need to make sure as a OS to have a fair mechanism of entering the critical section happens within a finite time. So it's not that they are waiting for indefinitely for a shared resource. So what are the design requirements? Any facility or capability that is provided, that is to provide support for mutual exclusion, should meet the following requirements. Only one process at a time is allowed. Then you should not by mistake allow two processes to enter a critical section. Process that halts or gets suspended in its non-critical section must do so without interfering with other processes. Suppose a process is not in the critical section, they get blocked, they should not indirectly affect some other process from progressing further. Okay, these are the software issues that you need to take care of when you are designing a multi-process systems applications. It must not be possible for a process requiring access to a critical section to be delayed indefinitely. I told you about that. When no process is in a critical section, suppose there is nothing, no process is there, you should still, okay, and any process that requests entry to the critical section must be permitted to enter without any delay. Okay, it's like locker room is free, but still you hold the customer thinking that there is somebody inside. Okay, that's a mistake that maybe a bank employee could do. Okay, so no assumptions are made about the relative speed. I already mentioned this. And a process remains inside the critical section for a finite time only. I told you that you cannot go inside the locker room and sleep, or a process cannot get into a critical section. A piece of code which is accessing a shared resource, a shared data, it should not call a block call, or it should not sleep inside. It should complete the job as early as possible and come out of the critical section. So what are the stages of mutual exclusion? Very, very simple. Before entering a critical section, you first of all, the user process knows which are the critical sections. Okay, OS does not know whether delete node has to be protected or not. Okay, or add node, that particular piece of code has to be protected or not. Only the user knows that this is, suppose if I am passing the same node linked list to which I am adding a node or deleting a node, it is to be protected. So that is to be that needs to be the knowledge of the developer, who is aware of which part of the code is accessing what kind of shared data. So I may have a one log. Okay, I'll call it as a log to make sure that only one process enters it for a linked list one, and maybe I will link list one is having a semaphore one, linked list two may be having a semaphore two. So I'll call it a semaphore, which is a locking mechanism, which I'll explain now shortly. So the association of the semaphore with the particular data, shared data, is the user process or the developer's responsibility, not the OS responsibility. OS will give you the key or will give you the semaphore. So it is similar to buying a lock from a shop. You are buying a Godrej lock. Godrej guy is not going to tell you that you have to use this lock only in your storeroom or not in the front door. Okay, it is your choice to decide. But you should know which key is for which lock and which room is this lock is actually fitted into, so that you can use it for a proper purpose. So that the relationship between the data which is being protected by the semaphore is with the user developer, not with the OS. OS job is to provide you the mechanism, and you have to make sure that relationship between the data which is being protected by a particular um, lock semaphore. So before you come into the critical section, like enter critical section, is some negotiation happens. It's not a very complex protocol as such, but it is a mechanism where you have to call a particular system API before you get into a critical section, and then you have to remember that you release it also. That means you have to put a code to make it release. Semaphore is a method of providing a mutual exclusion, which we are going to talk about it. Mapping of a semaphore to a shared data is application's responsibility. Application processes need to take care of acquiring the relevant semaphore before accessing the shared variable, because only the application knows which semaphores to be acquired to access a particular data. Application processes need to map a particular semaphore with a resource. Okay. Now, before we end this section, we just talk, get an understanding of what is a deadlock and what is a live lock. Two processes are deadlocked if each is holding a resource while waiting for a resource to be held free, which is being held by the other. So two processes are deadlocked if each is holding a resource. Okay, one process P1, okay, is holding a resource maybe R1. Okay, and now P2 is another process P2 is holding a resource R2. Okay, it is holding it and then it is waiting for a R1 to be released. Similarly, P1 is waiting for R2 to be released. Now, they will not release it unless the other resource is given to it, because they want it in one order. P1 wants it from R1 and R2 in that order, and it uses it and releases both R2 first and maybe R1 next. Whereas P2 wants R2 first and then R1 next. Now, what happens is this kind of scenario is a deadlock situation wherein it is holding a resource and then waiting for some other resource which is held by the another process, and it wants this resource. Okay, it's a deadlock situation, and this is a very famous problem where Chinese philosophers are sitting and then eating together, and they need to share the fork which is in between them. And if this is they can eat only when both the forks are available. Imagine a situation where two philosophers have one of these each, and then they will not get the other one because some other philosopher is holding it. So it is like you need both the resource to go further. So it's a dining philosopher problem, needs both the resources which both folk they need for eating. Now, what is a live lock? It's a deadlock situation. You understood it. What is live lock? Live lock is similar to deadlock, as I mentioned it, with an example of ball getting passed between two players in a football match. So except that state here, the states of the processes involved in the live lock constantly change. It's see, in a deadlock situation it is in a block state. Okay, processes are block state. They are waiting for some other resource to be released. They are not running. Whereas in the live lock case, two processes are in live lock situation wherein both of them are running but they are not making progress. Okay, so that's the situation of live lock. Okay, real world examples are, suppose if you are in a corridor. Okay, this is the middle, and suppose both of you are coming in this both the direction. Okay, now unless one person moves to the other side, this guy cannot go further. Now what happens in some scenarios, you might have experienced that both of us move in the similar direction. Now both are here. Now they made a move, but they still cannot proceed further. Now, what we realize that, oh, both of us moved on the same side, so we go back to the same situation, and again the people are again back to the same situation. So this is a live log wherein some change is happening, but it is not effectively helping us in making a progress. Okay, so deadlock recovery algorithms are there many. So have the risk of getting into a live log. So some deadlock recovery algorithms can get into a live lock thinking that they are relieving the deadlock, releasing the deadlock, but they get into a live lock situation where both of them are not able to make a progress. So suppose two friends are there and they want to exchange a gift, and one person takes out and they realizes that the other person also trying to take the gift out, so they hide it back. So in that case, what happens is both of them are trying to give the gift first, and they state they think about sharing it because other person is also trying to take the gift out. So this is a situation of live lock wherein both of them will never give the gift to each other. Okay, Okay, that's it. So let us last starvation, which is example of make, is normally caused by deadlock. In that case, it causes a process to freeze. Okay, it is one good example is CPU starvation. Another one is they don't get a chance to access their shared resource at all. Then they get blocked forever. Okay, so that's it. So see you in the next lecture. Bye bye.